My name is Doug Call, and I'm an associate professor in environmental engineering at North Carolina State University. And I'm here with our EPA P3 student team. Our team consists of myself, Professor Detlef Knappe, who's also in environmental engineering, undergraduate student Geoffrey Fylak, graduate students Yazeed Algurainy, and Elvin Hossen. I'm going to hand it over to them, and they're going to tell you a little bit about our project, what we've accomplished, and where we hope to go.
For our project, we focus on a technology for the point-of-use removal of per- and polyfluoroalkyl substances, or PFAS, from drinking water. PFAS are a group of emerging contaminants in water that are very persistent in the environment and may lead to negative health outcomes if consumed. The overall goal of our P3 project is to design, develop, and validate a regenerable point-of-use water filter to remove PFAS from drinking water. We focus on trying to make activated carbon, a common sorbent used in home water filters, work better to remove PFAS. To do this, we use a small application of voltage to electrically charge activated carbon so that it could better absorb PFAS.
We designed and constructed this electroactive granular activated carbon, or EGAC unit. It is a cylindrical unit made of graphite block housing to facilitate electrically charging and discharging the GAC. The unit consists of two beds of GAC, separated by a spacer, stacked in series. Raw water coming through the unit goes through the filtration process as it passes through the GAC beds, resulting in a treated effluent. When the cell is charged with electrical potential, each bed will function as electrodes that can absorb ions, enhancing total removal of ions from water. Stopping the electricity would result in ions being released back to the bulk solution and regenerate the GAC. We evaluate the removal of ions by monitoring the change in conductivity of the effluent. We have fabricated two EGAC units and conducted preliminary study using 10 millimolar sodium chloride solutions, which are model ions to first validate the system. Our findings showed, upon electrical charging, the effluent conductivity of the EGAC unit dropped below the influent conductivity, indicating the electroabsorption and removal of sodium chloride from the feeding solution. This primary result is proven to be promising, as it showed the feasibility of using an EGAC unit to electrically charge GAC and remove ionic species from water. For the next step in this project, we will test our EGAC with PFAS-containing water. We will focus on two common PFAS species, PFOA and PFOS. Adsorption enhancement through flow rate testing, cycle length adjustment, and voltage application will be evaluated. We expect our EGAC to successfully remove PFAS from water as it did with sodium chloride, and that improvements to the removal of PFAS compared to a non-electrically assisted unit will be observed.
We expect the EGAC to answer the challenge of developing a technology to ensure safe and sustainable drinking water. As an environmentally conscious innovation, EGAC is consistent with the P3 approach because it protects water quality by addressing major stressors that pollute drinking water, namely PFAS. The advantages of EGAC from its low energy requirement and waste reduction has exemplified the environmental character of this project, which supports the P3 mission.